Welcome to a new video in the video series on systems biology, digital twins, and AI. So this video is a continuation of the previous video on how to simulate ODE models by doing a quick overview of some of the other formalisms. So if we don't have an ODE in a state space form, how do we then get a simulation out of this? And this is a fairly non-in-depth video, again, just as when we looked at other model formalisms in the end of the formulation step. So it's a fairly short video. So if you have Boolean models that I mentioned in the other formalisms video, or rule-based models, which are a bit similar, but they are not necessarily just 0 and 1, but they are based on some kind of rules. Then these rules will contain some logical way of updating the system. So if you have a Boolean model, for instance, each nodes that are combined in the Boolean network, they will have a rule telling you how to update the value. So if you have some parents to the node that goes into it, which corresponds sort of to a reaction that is forming this, then if this one is 1 and this one is 1, then this one is 0. If this one is 1 and this one is 0, then this one is 0, and so on. So these type of rules you use to update everything. And then you have updated values, and then you do it again, and so on. So it's sort of logical rules that you just implement in the sort of algorithmic iterative way. So if you instead have DAEs, and you remember we encountered DAEs when we looked at these Windkessel or lumped parameter models. Those can sometimes become differential algebraic equations. Then you proceed in a similar way as in ODEs, but it's a little bit more complicated. So you need to use solvers that can deal with the DAEs. There are available such ones, especially for the lower index DAEs, which are sort of simple, you could say. So basically, the simple lower index ones allows you to approximately calculate an ODE that you can simulate in a normal way, but then you have some remaining algebraic equations that you might have deviated from. So then at each step, basically what you do is a correction step. So you see, are you fulfilling the algebraic equations? If you are not, then you need to modify the step so that you do fulfill the algebraic equations as well. And this you can do, for instance, using some kind of Newton-Raphson or root solver. And we will encounter those when we look at optimization. There are available softwares or available commercial algorithms for DAEs in a similar way as for ODEs. PDEs, partial differential equations. I mentioned those models, for instance, in connection to blood flow models, when you typically have partial differential equations if you simulate the full three-dimensional evolution over time. And basically what you do then is that you construct a mesh. So you subdivide the space into small areas, like triangles or small areas that you subdivide the space into. And inside each such area, you have an ODE. It's just that you have a transport between the set of ODEs within such little mesh point. So you have a set of coupled ODEs. And this mesh can either be static or it can be dynamic. And this is a whole field of itself. There are professors that only deal with how to solve partial differential equations numerically. So here existence of a solution at all, the speed of the solution, the correctness of a solution is much more of a crucial remaining unsolved problem than it is for ordinary differential equations, where it's almost solved. At least it's much more solved. But with this said, there are commercial softwares and open source softwares like Phoenix, for instance, that allows you to solve partial differential equations. So the final one that we'll talk about here is stochastic differential equations, where you have this type of stochastic components. And if they are based on reactions, then you need to solve something called the chemical master equation, which is a very hard to solve equation. So typically it keeps tracks of all of the individual molecules in the system, and typically you don't want to solve that because numerically that's very intractable. So what you do instead, and this is the only algorithm that we look at in a little bit of detail, is a simpler way to approximately solve the chemical master equation called Gillespie's algorithm. So this is something that you should remember. So Gillespie's algorithm was presented by a guy called Gillespie in 1977. But it was developed already in 1940 by Feller and Doob as a solution to the Kolmogorov equations, which are related. And basically there are two steps. The first is to calculate the time to the next reaction. And you do this by drawing a random number from an exponential distribution, where the time constant is given by the sum of the reaction probabilities. So we'll see an example on the next slide. And then you calculate which reaction that it is that happened at this time point by drawing a random number, pinpointing a specific term in the sum of all probabilities. So let's have a quick look just as at the basic principles of this, and then what the simulation can look like, so you get a little bit of a feeling for this. So here we have a very, very small system. A plus B gives the complex AB, and we have the dissociation of AB into the constituent parts A plus B. So we have a rate constant 2 and a rate constant B. So here we have, just as before, mass action kinetics. So this is just as before, but now we are in a stochastic domain, meaning that we assume that we can't describe this using an ODE that gives smooth and deterministic curves, but we have random processes about how the molecules move around. So we will have a stochastic simulation. And in step one, what we do is that we calculate for the A and B that we have, and for the values of KB and KF that we have, we calculate these reactions or reaction rates. So VF and VB. And these basically give the time constant for this distribution. And then you draw a number from this distribution. So if VF and VB together are big, one of them is big or both are big, then the time constant will be small, and it's very likely that we will have a new reaction happening very soon. And vice versa, if the sum is small, then the time constant will typically be longer. And then once you have decided when is the next time that a reaction will happen, then you simply go through the sort of portion of this total number, which is the sum of all the reaction rates, that you are in. So you draw a new number between 0 and 1, and this number will lie at some place that corresponds to a reaction. So if you are, so this VF is sort of the upper VF divided by R2 is the upper cutoff for it being the first reaction, and then if you're above that cutoff, you are, in this case, you are in the second reaction. But if you have more, you sort of subdivide the space between 0 and 1, depending on how big the reaction, how big part of the total of R2 that the reaction has. So if it is a big part, if it's the biggest reaction, the random number will most often hit that area between 0 and 1. So I hope this makes sense. You don't need to know very much details, but I just want to give you a sort of feeling for what this looks like. So here you see that you take steps. Here you can see the individual steps, and you see that there are sometimes very short steps. So here you have drawn a number that pi random happen to be a short time until the next reaction, whereas here it's much longer. And you also see that, so this is the time simulation of A and B, and you see that you sort of see some kind of behavior here, that it goes down and lays on a steady state, and here it also goes up and lays on a steady state. And this is probably what the ODE would tell you as well. But what you see here is sort of a much more random process, which corresponds much more to what you would see in an experiment if you have very few copy numbers. So here you only have 10 molecules in total. So you see that it's basically very few. So it's up to sort of the movement of the individual, the random movements of the individual molecules. Okay, so with this little sort of top level overview of some of the options for how to simulate other frameworks, we are done for this video of simulation in other formalisms than ODEs.